Hello there. So in this video you're going to see a more practical example with a patch antenna here on ANSYS Electronics. I'm with the student version here in case you are with the student version as well. So you can see that you can design a simple patch antenna with the HFSS student edition. This is version 2025 R2. I have already, for to just save time, I already created a project here and saved it on my computer, so we don't have to save it before we do it, so good practice there. And we have an empty project right there. So a patch antenna, it consists of I'm going to draw here, but briefly I'm going to then delete it. It will have something like the electric here, and then in the middle you have your patch, and this patch is your radiating element here. Just so there's some rendering issues here created. Oh, there we go. So this can be fed via microstrip over here or over there, depending on the rotation of your antenna, or via a probe. So if the probe coming from the bottom, a coaxial probe, which is what we are going to do today. The idea here is just to show a practical example using parameters. Lots of great tutorials on YouTube about designing a patch antenna, but very few with parameters, so I decided to create this one. So let's select everything here and delete. First, we need to determine the dimensions of our patch, right? So we need to select the frequency and the electric. Here we are on everything RF. So just for reference here, our coaxial connector, that's going to be our probe for the probe pad antenna. Usually has an inlet diameter of 0.9, and for a Teflon material with a dielectric constant of 2.1, we have an outer diameter of 3 millimeters, giving us roughly 50 ohms here. So those are the values, the rough values I'm going to use for this tutorial. The material I'm choosing here is the Rogers RO4003 with a dielectric constant of 3.38 and a dot dissipation factor or loss tangent of 0.0027. The thickness I'm choosing here is 0.813 millimeters, right? And finally, for the frequency of operation, I'm just choosing some WLAN channel here, and let's go with 5.805 gigahertz. This is the bandwidth of this frequency. I'm in the UK, so that's approved here. And yep, so we have all our parameters. Now, how do we determine our patch dimensions? I've created here a simple Python script that is going to show us how we have the calculation. The patch, as I designed before, it needs to have a width and a length, right? The length is going to be what will determine the frequency. W here is more for apologies, with impedance matching, also affected by the frequency and the permittivity. So we calculate based on the permittivity and the frequency that we want to radiate. We can calculate W, and from W we can calculate the effective permittivity here, because that's taking into consideration the patch, the air, the substrate, and the electric field that goes around it. And here's the formula for it. Finally, we can calculate the length of our patch antenna. And you can see here it takes the effective permittivity, the frequency we want to radiate, the width, and the substrate thickness. So you'll see a lot of places called H. My preference, I call it TS for thickness substrate, because when I'm designing with copper, I'll have thickness copper, thickness substrate, thickness shell, thickness of all of the stuff. So I prefer just my own design algorithm. So here's the formula for it as well. Feel free to pause the video here and copy it. You could have it on MATLAB, but Python is free for everyone, so we decided to create it on a Python script, just as simple. And because it's a Python script, I can simply open it and change the values for F0, ER, epsilon R, and the substrate thickness, the height. I'm not taking it from the keyboard just because I find it quicker to do it this way. So we calculate W, calculate then the effective permittivity, and then we calculate the length and print them up. Now let's run it here, and if I run Python 3 and I choose it here, I'm going to have the selected value. So our width here will be about 17.45 millimeters. Our I'm sorry, length is about 13.7879. You will find that this right here needs to be tweaked a little bit. We have a probe fed antenna, and this the position of the probe plus the length is what you adjust in the resonant frequency, as well as the impedance matching with the probe. So this needs some tweaking. And just for reference here, I'm putting the effective permittivity, just we need it later. We won't today. So let's go into HFSS and put in those parameters. I will have here, I'm going to import from another patch antenna design, all right? So just for the video to be faster, this is quite an easy thing to do. So just add your properties here and do it. In my case, I want to, is it here, HFSS and patch parameters. So the substrate width, I'm not going to change this one is good enough. Our substrate thickness here, TS, it's 0.813 millimeters. The W here for us is equal to, right there, 17.45. So 17.45. And our length, 13.78. Let's put 13.78. 13.78. This is the position of the feed, all right? So the feed is going to be parameterized as well, so on X and Y. On X, the length of my patch, I want it on the Y-axis, and the position of the feed, I'm going to change on the Y-axis as well. So for my X-axis, that's going to be 0, and the position of the feed, let's put it at let's look at -4 for now. Let's see if we have any issues with that. That's from the other design. Another frequency, another substrate, another thickness. This is the radius for the pin, so the diameter is 0.9, so radius 0.45. This is the height of the probe, 5 millimeters, and here I have the radius for my coaxial dielectric. In this case, the Teflon 1.5 millimeters. That's 3 millimeters in diameter. So I will click OK here. Now we have our parameters and we can design. So once you're dealing with the HFSS, as you see, if you're doing this for the first time, you probably will be seeing something like this, which I really don't like to do. But before we do this, also if you're doing this for the first time, you'll see this is on a terminal network, and we want to change our solution type here to model and press OK. Now we have a model network, and finally let's go ahead and design. Again, I'm going to click here on the draw box. I don't want to draw like this, and if you see in the bottom, using F3, F4 to toggle between point and dialog mode entry, I want the dialog, so I press F4. And now I'm going to write the dimensions and the location for my substrate first. So the position for my substrate, I want the center of the substrate to be in the origin of my coordinate system. So I'll put here the width of the substrate is WS divided by 2. So I put it negative, so it goes on the left first on the X, and on the bottom of the Y-axis divided by 2. And the position for the substrate is going to be on the 0 on the Z-axis. X size is going to be WS. Y size WS as well, and Z size I'm going to put here -TS, so it grows downward on the Z axis. Attributes, I'm going to call this my substrate, and on material I'm going to add it, and I'm going to look for my Rogers material, You see here that it has the 4003, not exactly the same as the one we have on our data sheet. So I can clone this material. I'm going to not copy, but add here C and change our permittivity to 3.38. So here 3.38, and our loss tangent is 0027, which is the same as the other one, and I'm not going to change the rest here. I'm going to press OK. Now we have our Rogers RO4003C. Yes, that is in the model, wireframe display, and I want to give it some color, so choosing this color here. Press OK, and now we see this gigantic thing. I can just pre-select fit selected, and there we have it. That's our substrate. Now, to simplify and save simulation time, I'm going to use the metallic parts with a perfect electric conductor, and whatever I can use a sheet for it to put on top, I'm going to use a sheet. So to draw a rectangle, that's going to be first my ground plane. So let's draw the ground plane. The ground plane has the same dimensions as my substrate. So minus WS over 2, minus WS over 2, and the position, because it's a ground plane, is going to be on the negative. Oops. Oh, I just lost whatever I had done. WS over 2, minus WS over 2, and here is going to be minus TS. So it goes in the bottom. The width is WS, and the length is WS as well. Attribute is going to be my ground, and color, I'm going to put some copper color here. Okay, and we see here at the bottom. I'm going to assign boundary conditions later. Now let's draw our patch. So our patch, the position now for the patch is minus W over 2. For the X, the length is on the Y-axis, so minus L over 2. And the position on the Z-axis is 0. The width is W and the length is L. And there we go. This is going to be my patch. And I am going to change the color here to be the same as the ground plane. It's a copper material, so just giving some orange color. And we have our patch here. Now, with regards to our feed, it's going to be parameterized, and I need it to dislocate it and at the same time everything that's related to it to be attached to it. So the first thing I am going to do is I'm going to draw, in this case here, let's draw the center pin of the coaxial cable. I'm going to draw a cylinder, and the cylinder is going to be my center pin. The center position of my pin, remember I chose to be XF for feed, and YF for the feed position on Y. And my pin here, it's going to start from the bottom and it's going to touch this this patch. So I lost everything again now that I'm drawing my mouse here and I'm losing it. So XF, YF, and in my case I have the thickness of the substrate minus TS minus the height of the pin. The radius of the pin is the pin radius. The height is TS plus HP. Number of, so you can see here, if I am to look over here, this from here to here is HS, and from here to here is my TS. So HP here, HP from here to here, and then TS from here to here. Number of points, that's going to be 0, so it's a perfect cylinder, and this is my, let's call center pin. And if you're watching this and see that I'm typing center wrong, I'm sorry about the. So PC here is my perfect electric conductor, and see it has two of the same materials here. They have the same bulk conductivity is extremely high, and I am going to choose it to be it. Color, I'm going to give it like a yellow, so it's like a golden color-ish from the coaxial connector. And now I have my coaxial pin. And finally, I need to draw the dielectric. So for the dielectric to follow along with the pin, if I need to move the pin location, I'm going to choose a pin like so, and I'm going to click here on Object Coordinate System, and I'm going to choose the center of this pin. Now my dielectric is going to follow around my pin wherever it goes, which is wonderful. That's exactly what I want. Now the height for my dielectric, it goes from here to the substrate. It doesn't go through the substrate, only the pin goes through the substrate. So it's going to be HP. Okay, let's draw another cylinder, and the position now it's in relation to Object Coordinate System 1, which is this. So it's in the center. Perfect. We don't need to change that. The radius is going to be, we have already determined this, which is R coax. I know my name is King, went a bit off there, but that's what we have for today. And the height for it is HP, and you can see we go from here to here. Our limit is the ground plane. Attribute, this is going to be a cylinder. This will be my call it dielectric coax. And for the material, let's choose here Teflon. It's 2.1. And a color for it, it's roughly white, right? So I'm going to give some grayish color around here. Press OK. Hopefully we'll be able to see it. And there we go. Yes, we can kind of see it. Yeah, there we go, especially in contrast with the copper here. And I'm going back to my coordinate system, the global one. There we go. Now, a few very important things. We need to assign some boundary conditions. So I'm going to choose select face over here. And in this case, I need to choose the outer face of my dielectric for the coaxial cable. You see it only selected the face, the outer face, and I'm going to assign this as a assign boundary. This is going to be a perfect conductor, so perfect E. And I need also, those two are faces or objects, so it doesn't matter if I press O, you see it changed here for object. I can select this and pressing Control and holding it, I select the other one. And again, assign boundary, perfect E, and we have our materials over there. So they're all assigned. Now we have an issue. If I were to come to simulation and validate, you see that I have a few problems there. One of them is that things are intersecting. So I need to subtract the pin from my dielectric. So I'm going to choose the dielectric first, and then the center pin, pressing Control. And on draw, I'm going to click on subtract, and I want to keep the center pin, so I click on this button. There we go. We have a center pin, and you see the hole here in the dielectric. So the center pin can go through, and the same thing will be for the patch and the substrate, and also the ground plane, but I'm going to leave the ground plane for last because it's also going to be subtracted by the coaxial dielectric material. So choosing those two and choosing my pin, center pin here, I'm going to subtract, and I'm going to leave the blank parts to be the patch and the substrate. I'm going to move to the left side, so I'm going to subtract the center pin from both of them. I'm going to clone the center pin, and there we go. Now the patch has the hole for the pin, and the substrate has the hole for the pin. And the ground, finally, I can choose the ground, I can choose the dielectric, I can choose the pin, and I can, again, subtract, and I just want to keep the ground on the blank part and remove the center pin and the dielectric from it. So I'm going to clone the tools, and now we have the hole here for our ground plane. And there we go. Now, before we set up our radiation box, let me remove those arrows here. Oops, those arrows here. They're not very important to us right now. Before I put my boundary box, I'm going to first come into the analysis, add a solution setup, and we're going to choose advanced here. And again, I want 5.805 gigahertz. Number of passes, let's put like maybe 14 here. Delta here, let's put 0.02. So it's going to converge when 2% difference between steps. I'm going to press OK here. And under setup, it didn't prompt me to do a sweep, so I'm going to add it here, frequency sweep. And that frequency sweep will go, let's say, from 4.8 gigahertz. Goes together here, so I'm going to put together, and 6.8 gigahertz, and step sizes of let's put 0.1 gigahertz instead of 0.1. So 21 points defined actually. Now let's increase this to 0.01. There you go, 201 points. That should be enough for us. And save fields, because we want to see the radiated fields and maybe the electric field too. Now I can come to model here. I'm going to right click on it and create open region. You see the frequency that we have chosen here. And just because this is just a touch antenna, it could use the radiation here, but PML is more robust. I'm going to press OK, and we have our radiation box. You can see it automatically created our radiation spheres as well, so we can plot the far field for our material. Now, if I come to simulation and validate, boundary excitation, of course, I forgot the excitation. So let's go back in here. I'm going to hide, so press Ctrl H on the radiating surface. I'm going to press F for face. So see here, I have selected face, and I'm going to click here, right click, and assign excitation, a port, and I'm going to assign for this project a wave port. The integration line, I'm going to put here on the line, and let's follow from the corner of my center pin here. So we have the center pin, so it touches the center pin, and the perfect electric material on the edge of the dielectric that we have defined there. We want to specify a direction, and we can see here it's going up, so it's correct. I don't need to flip it. Next, I'm going to normalize to 50 ohms and press finish. Now we have our antenna that should be finally ready to simulate. There we go. It passes everything. I'm going to clear messages. If you want to set up another solution, you can do it here without any problem. Again, let's say it's 5. Let's see what happens on one of the edges here for 5.795. Okay, 7.95 and 5.815. So, oops, sorry. 795. Let's just choose this one to be practical. All right. 12 here, and I'll press OK. Now it's asking. Yeah, let me change something here. Let me delete this setup, and resolution setup advanced. 5.805. Number of passes is 12. Now the delta is 0.02, which is all right. And press OK, and there we go. So I want this to be from 4.8 gigahertz to 6.8 gigahertz and 101 points just to be quicker. Save fields, and it's interpolating. Yeah, now I don't know what I clicked. wrong last time. All boundaries are still here, yes. Simulation validate, everything is alright. Now let's run the simulation finally. Save it and run the analyze all. This shouldn't take too long, right? What we will see, just while it runs, what am I expecting from this result? Will it match perfectly at 5.805? No. We are choosing those analytical values for our patch antenna, but on a practical term, especially when you have a center pin, those are more like guidelines. We can keep the width the same, but we will need to tweak the length probably to reduce that length to something that is going to resonate better at the frequency that we want, and also to tweak a little bit the frequency of our, or not the frequency, sorry, the position of our center pin. Now it is finally simulating, it must have converged. If you want to see if it converged, you press on setup, right click, convergence, and you can see that it converged on the 11th path. And now we have our results. Let's click on results here. You can right click or you can come to results, go to solution set report. 2D, I want to see the S parameter S11 in dB. I will press new report. And we are about there, but not really. If I right click and see on marker for an X marker, and I position it, so I'm going to double click this at 5.805. We will see it right here. Our impedance matching is quite poor. So let's do some tweaking, and let's see what we can do here. Let's put this length here to be, let's say 13. So right now it's resonating at a lower frequency. We want to bring it to a higher frequency. Therefore, our patch needs to be smaller. Remember that it depends on the wavelength. So I'm going to click here on my design, and let's change this length here to 13.4. And the position of my feed here, I'm going to change to minus 3.4. So it's about like a third of the way, or a bit more than a third of the way from here to the center of the patch. Just for my conscience to be clear, I want to clean up all the solutions, just to avoid overlapping with the old one. And I'm going to validate, everything's alright, and analyze all. So there are a few considerations here while the second simulation is running. The first being the position of the feed. If we look for patch antenna feed position, usually Optimum does have great resources here, and we can see it over there. There are some considerations. You have this formula here, X for the pin. In our case, we are only L, right? Not X. And this is a function of the impedance of the patch. Is that correct? ZP. Now I will admit I forgot from this article what it calls ZP and ZA. You can see here that it does. You do have some rough calculation that you can use for this. And the second one is the thickness of your substrate. So our substrate here has a thickness, and we have our pin that goes from here to here, and with signal around the dielectric, right? If you make this substrate too thick, you are going to increase the length of this pin, and you increase the inductance of the pin as well. So you may need to compensate for that. Now let's look at our result. It is ready, and voila, 5.805. We have minus 10 dB. Not ideal, not perfectly there, but let's consider it for this tutorial. So the bandwidth here is from let's consider minus 10 dB, 5, 8, 2. So does it comply with 815, 8? So it is within the bandwidth of the channel that we are pretending to work here, and this is the default rate. Now, if I want to see the far field, I can similarly come to results, far field reports, and click on 3D polar. Let's see first the directivity here, choose dB, and geometry 3D from the last adaptive here. Primary sweep is phi, the secondary sweep is theta, and I'm going to press on a new report, and then we have our patch directivity plot, about 7.34 dB. Now, because we are working with a material that has dielectric losses, we can plot the gain as well. Press dB here and new report, and we have here a gain of 702, so we lose a bit of on the directivity. And if we want to consider your impedance matching, so the S11 not being perfect, you can click here on the realized gain and dB and press new report, and you are going to see it reduces a little bit more. And finally, if you want to see the directivity plot, but them being on a 2D field, so you can have here magnitude on a polar plot. Not the geometry here is not going to be 3D. I'm going to click on the elevation, and elevation here is going to be theta, and the families you can see here for phi, it's going to consider phi 0 and 90 degrees. So I'm going to generate the reports first, and then we're going to analyze it. So let's put here dB. Let's just consider the gain for now. Press new report, and we have the two cuts. What are those two cuts? If I have a look here, you see phi equal to 0 degree, and theta here equal to 0 degree. So if I go from theta is my elevation cut, so if I cut on theta like this, and I take this plane here from theta to 0 and going around to here again, I will have my phi 0 cut. If I'm looking from this cut over here, so theta going around here at 90 degrees, I have my theta with my phi cut, which is what I can see on both plots. So this is it for this video. If you want to see the field overlay over the antenna, you can do it. So plot fields, the radiation field, and let's say, okay, I want to see my gain plot over here, and apply. You can see the gain plot over the antenna, which is quite cool. And secondly, to remove it from here, if you want to see the electric current over the antenna, you can come to plot fields, actually select the surface first, right click, plot fields, J, and the surface current here, and that's the frequency we're interested on, and I'm going to press done, and there we have it. You can animate it if you want, so I'm going to right click on it and animate, and I want to change the phase here, so let's say from 0 to 170, let's make it quite smooth, let's say every 5 degrees, and press OK, and I press animate. You can see it going like that. It actually had a pretty poor resolution here. I'm not sure why. Maybe I did something wrong. But anyway, that's how you can animate the field. And I'm going to stop it and bring it back to 0. And if you want, so this is going to be here permanently. If you want to hide it, you'll press right click here, plot visibility, and it's going only to show when you click on top of here. Pay attention here on the scale as well. Alright, so this is it for this video. I'm going to save it, and if you want to follow along, follow, or you can use this as a base for your own design as well. Right, bye bye.